All right, so let's actually go ahead and jump forward a few years and look at another approach to digital signatures, the so-called ElGamal digital signature. So as with the RSA world, we know that sometimes we can take some of these very nice public key crypto systems, make a few slight modifications, and actually rebrand this thing as a digital signature. So if you remember way back in the days of looking at the discrete log problem, we actually first saw one of these nice public key crypto systems in the world of the ElGamal public key crypto system. We actually first saw the Diffie-Hellman public key exchange, and then immediately afterwards actually presented this thing as a public key crypto system before we actually looked at the RSA side of things. It was the one that was a little bit out of order, but it fit very nicely after seeing all of this discrete log stuff. So now we're actually going to jump back to it, but now view it as a digital signature. So just like its kind of version as a public key crypto system, the security of this thing is going to be connected to this question of whether or not we can solve a discrete log problem. So since we're talking about a discrete log problem, a lot of the terminology and the notation of that world comes back into play. That is, we're going to have things like order and primitive roots and generators all come full circle again. So if it's been a little while since you've thought about those things, kind of hopefully you'll have kind of a quick reminder of what those things are all about. The idea is that we're going to be starting with some classic big prime P, and we're going to look at some entry which we're going to call G. We know that if we were to take G and begin raising it to various powers, at some point in time, it's going to turn into a 1. That is, we know that if we took G and raise it to the P minus 1 power, it's absolutely going to turn into a 1 mod P. That is Fermat's little theorem. So we know that it eventually will turn into a 1. The question then comes into play as to when does that actually happen. So the very first time that it emerges as a 1 is then going to be referred to as the order of that number G. So what we're going to be interested in is we're going to be interested in those entries G that are going to have that full order, that number of P minus 1. Those objects that have order P minus 1 are going to be referred to as primitive roots or generators. And those are going to be kind of the things that we want to see. The larger the order of that entry G is going to be, we know that it's harder to actually solve this discrete log problem. And you can see that at this stage right here, that the discrete log problem is actually going to be connected to trying to break what this kind of nice little signing key is all about. So if you can solve the discrete log problem, you can begin to assume the role of Samantha or the signer, and you can begin sending all kinds of junk all over the place. So the overall process is the following. So we have our two players in play. We have Samantha or Sansa or our signer. She's going to be taking some documents. She's going to be signing them, and she's going to be sending them off to Victor or Vladimir or the verifier. The way that this is going to be structured is a little bit more complicated than the RSA side of things, but as I mentioned before, it's a very nice springboard into the world of modern signatures. So there's kind of a couple aspects that are going to start on Samantha's side of things. She's going to have to create some keys. She's going to take her document, and then she's going to sign it. And then Victor is going to take all of that information, and he's going to have to verify it. So before any of that actually starts, there's going to be some third party that's actually going to release into the public this large prime P, whatever they want it to be, and one of these entries G that are going to be a generator or a primitive root modulo P. So both Samantha and Victor and anybody else in the entire world knows what that little pair of numbers are going to be. So Samantha on the signing side of things are going to start up by generating this nice signing key. So just like we saw on the RSA side of things is that we're going to have some object that's going to be connected to creating signatures. What we're going to see is we're going to take that little a, which is going to be a randomly generated number, and we're going to create this capital A, which is the exact same first step in the ElGamal public key crypto system. It's also the same step in the Diffie-Hellman public key exchange. So we're going to, we're back to the idea of we're taking some paints and we're going to be mixing some paints. So what we're going to do is we're going to take that little number G, we're going to raise it to the 8th power, this private little a, and we're going to release to the world this capital A. You can see then at this point in time that if you were the evildoer, you know what the capital A is going to be, you know what the little g is going to be, and you know what the little p is. So you have a nice little exponential equation that you're going to try to identify what that exponent is, which is then going to be connected to a discrete logarithm. So if you can solve the discrete log, you automatically know what this signing key A is all about. So we're again hoping that that problem is genuinely a hard thing to solve. So now we move to the signing stage. So just like the RSA side of things, we're going to take some random document D, which is usually going to be the hash of some giant massive file D. So it's something that I can easily sign without having a massive signature associated with it. So you grab your D, whatever that happens to be. You're also going to have to generate another private exponent, which we're going to call E. This particular E is going to be a one-time use E. And you're going to see this in some of the activities and homeworks, is that if you were to use the same E on multiple documents, things become really easy to break. So you don't want to use the same E more than once. So it's a one-time E. You have this D, you choose an E for it, and you forget about that E afterwards. So that becomes your kind of initial stage in creating kind of all of the tools you need to do the signature. So it's kind of you now got your sheet of paper, you got your pencil, you got your little rubber stamp, you got all the stuff that you need to do the signature. Now you got to go full-fledged and actually create the signature. The first thing you're going to do is you're going to create this little value S1. So the signature is a two-part signature here. The first thing you're going to do is you're going to take that number G, so that publicly available, everybody knows G. You're going to raise it to this new little exponent E, and you're going to reduce that number mod P. So that's going to be part of your signature. The other part's a little bit more involved. So what you're going to do is you're going to take this document D, you're going to subtract off A times the number S1, and then you're going to multiply it by E's inverse, and all of that's going to be viewed modulo P minus 1. So the moment you see something that says E inverse, you need to kind of have in the back of your brain making sure that that particular object is actually invertible. What that means is that the number E has to play nicely with the number P minus 1, which is to say that the GCD of this E and P minus 1 needs to be a 1. So this one-time E is not completely random in that it can't just be any random number from 1 to P minus 1. It has to be specially chosen so that it plays nicely with P minus 1. So since P is prime, we know that P minus 1 is going to be even. So this little E cannot be some even number. So it's going to be an odd, and it can't have any of the factors that P minus 1 happens to have, which is a pretty easy thing to do. You just generate the E until that object kicks out something that is a 1. Okay, so that becomes your S2. Those two things, S1 and S2, get shoved off into the world. And then we can actually assume the role of victor and actually try to begin this verification process. The verification process is a little bit more involved than it was before. So you got to think about everything that Victor knows about. Victor knows the A, that first part from Samantha's key. He knows the document D, so you can see that, whatever Sam or Samantha is wanting to present. We know the two parts to the signature, so S1 and S2. And he also happens to know the values P and Q. So I tried to keep this that anything that was written in green is publicly available, and anything that's written in S is actually the private stuff. So we have 6 random things that Victor has to play with, and now he has to somehow merge them all together to see if this thing is properly verified. The way that he's going to compute this is the following. He's going to take that number A, he's going to raise it to the S1 power, and then multiply that object by S1 raised to the S2 power, and reduce that whole thing mod P. The question then comes is whether or not that thing is the same thing as G raised to the Dth power mod P. If it's congruent, then we know, yes, this thing is properly verified, and if it's anything else, it's going to be a fail, and we know that this signature is not valid.